All right, let's take a look at the function f of xy equals x squared minus 2xy plus 2y squared. This is not in your notes, so you might need a separate piece of paper for this. So let's start off by just finding the partial derivatives. So pause the video, find these partial derivatives, and start it when you're ready. All right, so hopefully that went pretty well for you. If it didn't, reach out and let me know. So now what we want to talk about are higher order partial derivatives. In other words, taking the second derivative. So if I want to take the second derivative, in our past experience, we didn't really have to worry about what we were taking it with respect to. But now we know that even taking a first derivative, I have two options. When I'm doing partial derivatives here of a formula with two input variables, I have two options, and we haven't talked a lot about this yet, but we'll do some examples here. Maybe we even have a function with 3 inputs and 1 output. Well, then we could find the partial with respect to x, we could find the partial with respect to y, we could find the partial with respect to w. So we have lots of options for our first derivative. So that means, from the first derivative, I could take the partial. I could take this derivative and then take the partial with respect to x to that. Or I could take this first derivative and take the partial with respect to y. Similarly, I have this partial with respect to y. I could take that and take it with respect to y again. Or I could take this partial derivative and take it with respect to x. So we really have 4 options for the second derivative. And so this is the notation for these. These are 2 different types of notation. So I was using this second notation here in the example I was just showing. So f partial x, or we could just read it fxx, is saying you're going to take the partial derivative with respect to x and then with respect to x. So it's working from the inside out. So where you have to really pay attention, although we're going to see that these are mostly the same, we'll get to that in a minute, is when you're taking the derivative with respect to y then respect to x, or with respect to x and then respect to y. These order matters here. Okay, it's telling you to do something different. Right, this first one is telling you to take the derivative with respect to y first and then take that answer with respect to x. And then this notation is a little more, more symbols, so to speak, but let's just look at one of these. So this notation is analogous to that notation right there. The partial derivative of f with respect to x. Okay, so I do that first. Then I get this answer. Now I want to take that answer and take the partial with respect to x again. So that is this piece right here, which is shown in this other notation like that. Okay, and then we can simplify this notation to be d squared f over dx squared. Okay, and then all the rest of the versions here. Now the actual computation of this thing is pretty straightforward. We're just going to do the stuff that we did before. All right, so for this guy, if I want to take the partial with respect to x again, then I'm going to take the derivative. Let me make a little more space here. I'm going to take the partial derivative with respect to x of 2x minus 2y. This business is this business, and this business is this business right here. All right, well, that's pretty easy computationally. The derivative of, see how maybe it's just me, like this d looks like that too so much. I need to do my 2's different or something. Anyway, okay, so the derivative with respect to x is just 2, and then that's a constant, so the 2y I treat like a constant, so I just get 0. All right, let's try this one. So now we're going to take the partial derivative with respect to, maybe I won't connect these, that might be good, respect to y of 2x minus 2y. Okay, so now 2x is a constant. That's going to give me 0, and then the derivative with respect to y of the second term is just negative 2. All right, why don't you try these? So take fyx and actually let's do fyy and then fyx. Maybe pause the video and then start it up when you have your answers. All right, let's see how you did. So this, we're going to take the derivative with respect to y of negative 2y. Oh, what, this isn't supposed to be y here, is it? You probably caught that, huh? Let's see. This guy, one of these should be an x up here. So the derivative with respect to y, that's a 0. And then the derivative with respect to y of this, my constant, is negative 2x. Did I say x and write y? I'll have to go back and listen to the video and see. Let's try that. Okay, sorry about that. All right, so now with respect to y of negative 2x plus 4y, that would be 0, and that would be a, so let's write this down. That would, the first term would give you a 0, and the second term would just give you a derivative of 4. All right, so then we're going to take the partial with respect to x of the partial with respect to y, which was that guy, and so that's going to be negative 2 for the first term and 0 for the second term. All right, so what we notice in this example is that the partial xy, actually we don't have to write those parentheses, the partial xy is equal to the partial yx. Negative 2 equals negative 2. Let's try another one and see if that works as well. All right, let's try h of xy is equal to the square root of 4 plus x squared plus y squared. So what I want you to do is I want you to find fxy and fyx. So make sure you do those in the order that they are notated. So for this first one, you're going to do the derivative, partial derivative with respect to x first, and then whatever answer you get, you're going to take the partial with respect to y. For the second one, you're going to take the partial with respect to y, and whatever you get for that, you're going to take the partial with respect to x. So I'm going to go ahead and write out the partial with respect to x and y. I'll start the video, I'll pause for a minute, and then I'll just do that part before we do the second derivative part in case you want to check yourself. Okay, so you can pause the video and start it if you want to see the inside part here. All right, so this is what you should get for partial x, partial y. I put f over here, but since I labeled it x, or h, we'll label it like that. Okay, so double check these before you go do your second partial. Make sure that you've got these right. Now you may have written that negative 1/2 as a fraction with a square root underneath. I know I'm going to do the derivative again here. I prefer to use the product rule over the quotient rule. I just find it easier. The quotient rule seems like a lot. So for me, if I'm going to do partial x, y, I would rather do the derivative with respect to y of x times 4 plus x squared plus y squared to the negative 1/2 and use the product rule personally. All right, but why don't you go ahead and give that a try, and you can restart the video when you have it. All right, so I'm going to use the product rule. So I'm going to do the derivative of the first, the derivative of x plus the second thing I'm multiplying here. Now I'm doing the derivative with respect to y, so x is a constant. So the derivative of x here is 0 because that's a constant. Okay, so I'm not even going to write the second thing. It's going to be 0. So plus, and then I'm going to have my first factor times the derivative of the second one. So that's going to be negative 1/2 times 4 plus x squared plus y squared, subtract 1, negative 3/2. Chain rule, derivative with respect to y of the inside part, which is just going to be, this is going to be 0, 0, and 4y. Wait, that 2 is not supposed to be there. Let's take that 2 out. That's not. There we go. 4x squared plus y squared. I think I was getting ahead of myself doing the derivative. Writing that 4 there. Okay, 2y. There we go. All right. So this 2 is going to end up being able to cancel with this 2 here. So we are going to end up with negative xy on the top. And now we can move this stuff to the bottom. I'm not going to write it as a radical. I'll just leave it as to the 3/2 power. But you could write it as a radical if you want. All right, well, you should get the same thing when you do h, y, x. So let's give that a try. And again, if you haven't done it, I'd encourage you to pause the video and try it yourself first and then check it out. Of course, you'll know if you have it right or wrong because it should come out the same in this case. So again, I'm going to use the product rule here. You could use the quotient rule if you like. So the derivative of the first factor with respect to x, since this is a y, is going to be 0 again. So I'm not even going to write the second one. Plus, then I could do the first times the derivative of the second, which is negative 1/2 4 plus x squared plus y squared to the negative 3/2 times the derivative of the inside piece here with respect to x this time, partial with respect to x. That's going to give me 2x. So you see a similar pattern to what we did before. All right, and then these 2's are going to cancel. So I'm left with negative xy all over 4 plus x squared plus y squared to the positive 3/2. All right, well, it's going to turn out that for most of the functions that we're looking at, that fxy and fyx are going to come out to be equal. There is a criteria here. Assume f is defined on an open set D of R2. So we've got some domain R2. So our R2 would be, this xy plane. And f is defined on some, let me use pink again because we were using that before, some open set D. So I've got some D here. This may not be the entire domain, but it's at least I know it's defined in there. I know that my function has outputs for those particular inputs. And if the function, if we get an fxy and an fyx that are continuous in this pink area here, then they're going to come out to be the same value. So if I'm looking at, say, this function right here, it's continuous everywhere except for, well, actually everywhere with that 4 in there, right? I was going to say except for 0, 0, but with that 4 in there, that's positive. Those are going to be positive. So this guy's continuous everywhere. Then I'm going to expect that it will equal f of xy because this is continuous. And similarly, f of xy is continuous as well. Certainly that first one that we did, domain is all real numbers for this, and we did all the partial derivatives, and all the second partial derivatives came out to be constant. Certainly those are continuous everywhere, so we would expect that the mixed partial derivative is what they're called would come out to be equal. Okay, these are called the mixed partials here. So really what we're saying is that if these mixed partial derivatives are continuous on a certain domain, then the order doesn't matter. I mean, I don't want to say that. The answer will come out to be the same. Certainly if you're asked to compute these two things, the order in which you do them matters, but they will be equivalent. Okay, now we're not saying anything about these guys over here. We're not saying anything about fxx or fyy. We're only talking about fyx and fxy, those mixed partials. Now, do you remember what second derivatives told you about functions in one variable, two-dimensional functions? The second derivative told you about concavity. So there is an analogous application here, or connection, regarding the concavity of a three-dimensional figure, which we're not going to look at too much, but that is the connection. So that pretty much wraps up the important parts of 15.3. I think the only other thing I might want to do with you is one example that has more variables than just x and y. So let's look at f of u, v, w. So 3 input variables and 1 output variable. And that is u over v plus w. Okay, so if I want to find a first partial derivative, I really have 3 options here. I can find the partial with respect to u, the partial with respect to v, and the partial with respect to w. So if I'm finding the partial with respect to u, then I am going to hold v and w constant. Okay, so I'm going to think of these as constants. So this is like u over some number. All right, so what would the derivative of u over some number be, like u over 5 or u over 7? It would just be 1 over that number, right? So the derivative, partial derivative with respect to u, I feel like I may have lost a couple people there. You could think of this function as, if you're thinking of it as u as the function, you could think of it like this. Right? So it's almost like 1 over v plus w is a coefficient of u, if you're thinking of u as your variable. Okay? So then the derivative of that would just be the coefficient with respect to u. All right, I think that might have helped. Let's try finding the derivative with respect to v. So now I'm going to consider u and w as constants. So it could be some function like 6 over v plus 7, something like that. How would I approach that derivative? So me personally, I would approach it by thinking of this as like u times v plus w to the negative 1. And I would use the product rule. Some of you would use the quotient rule. That's fine. You can do that. Okay, maybe I should show it. I'll do the quotient rule when I do with respect to w. So I'm going to do the product rule here with v. So I'm going to take the first, which is just a constant, times the derivative of the second. So that's negative 1 times v plus w times the derivative, partial derivative, with respect to v of v plus w. Well, that's just going to be 1, right? We'll come back and write that down. Plus the derivative with respect to v of u times v plus w to the negative 1. Okay, so let's see what we get here. We're going to get u times negative 1 times v plus w times 1 plus 0, and then all this. The derivative, this is constant. U is constant, so that's 0, so that doesn't matter. All right, so we're going to end up with negative u, how do we want to write this? Negative u times v plus w. Oh, that's supposed to be to the negative 2. Gosh darn it. Sorry. This is -1. I do the product rule. That should be to the -2. That should be to the -2. Okay, so then we'll write that as a fraction. V plus W -2. Okay, maybe you want to try this one. I'll do this one using the quotient rule. So I'm going to write it as the derivative with respect to W. If you want to pause the video and give it a try, however you want to do it. All right, so using the quotient rule here, we would get the bottom times the derivative of the top with respect to W is going to be 0, minus the top times the derivative of the bottom with respect to W is going to be 1, all over the denominator squared. Maybe the quotient rule is a little easier for this one. I wouldn't have forgot my -2 doing the quotient rule here. All right, so the first part comes out to be 0, so I get opposite of U over V plus W squared. Could you do second derivatives? Sure. You could do second derivatives as well. We're not going to do it on this video right now, but I could do, I could do that. So that would mean I would take the derivative with respect to V of what I got for the partial when I took it with respect to W, and I'd have to do all that, which we're not going to do. But I just want to make you aware that these techniques are applicable to functions with more than 2 input variables.